Process of sedimentation. Sedimentation is a process used in various scientific and engineering fields, particularly in environmental engineering, water treatment, and geology. It involves the settling of particles suspended in a liquid under the influence of gravity. Here's a detailed overview of the process. Principles of sedimentation. Gravitational force. Particles suspended in a fluid experience a downward force due to gravity, causing them to settle at the bottom over time. Buoyancy. The fluid exerts an upward buoyant force on the particles, counteracting gravity. The net force, gravity minus buoyancy, determines the settling velocity of the particles. Drag force. As particles move through the fluid, they experience a drag force that opposes their motion. The drag force depends on the shape, size, and velocity of the particles, as well as the viscosity of the fluid. Terminal velocity. A particle will eventually reach a constant speed, terminal velocity, where the gravitational force equals the sum of the buoyant and drag forces. Steps in the sedimentation process. Flocculation, optional sometimes, particles are too small to settle quickly. Chemicals called flocculants may be added to cause particles to clump together into larger aggregates, flocks, that settle faster. Settling. Particles begin to settle at different rates based on their size, shape, and density. The larger and denser particles settle faster than smaller, lighter ones. Clarification. Clearer water rises to the top as the particles settle to the bottom. This layer of clear water can then be drawn off for further use or treatment. Sludge collection. The settled particles form a layer of sludge at the bottom of the sedimentation basin. This sludge can be removed and processed separately. Types of sedimentation. Discrete sedimentation occurs when particles settle individually without interacting with each other. Typical in processes involving sand or larger particles. Flocculant sedimentation involves the settling of particles that clump together to form flocks. Common in water and wastewater treatment where chemicals are added to promote flock formation. Zone sedimentation occurs when particles settle as a zone or blanket, creating a clear interface between the settling particles and the clarified water above. Compression sedimentation happens when the concentration of particles is so high that the lower layers of particles are compressed by the weight of the particles above them. Applications. Water treatment. Sedimentation is used to remove suspended solids from water, reducing turbidity and preparing it for further treatment processes like filtration and disinfection. Wastewater treatment. It helps in removing solids from wastewater before biological treatment. Mining and mineral processing. Sedimentation is used to separate valuable minerals from ore. Environmental science helps in studying sediment transport in rivers, lakes, and oceans. Factors affecting sedimentation. Particle size and density. Larger and denser particles settle faster. Fluid viscosity. Higher viscosity slows down sedimentation. Temperature. Higher temperatures reduce fluid viscosity, enhancing sedimentation rates. Particle concentration. Higher concentrations can lead to hindered settling due to interactions between particles. Mathematical models. Stokes' law, used for calculating the settling velocity of small, spherical particles in a fluid. K1ch theory, used for zone settling where particles form a settling zone. Conclusion. Sedimentation is a critical process in various fields, enabling the separation of particles from fluids. Understanding the principles and factors affecting sedimentation helps in designing effective systems for water treatment, environmental management, and industrial processes. Formation of process of sedimentation. The formation of sedimentary layers through sedimentation is a fundamental process in geology that contributes to the formation of sedimentary rocks and landscapes. This process involves the deposition of material transported by water, wind, or ice, which then settles and accumulates in layers. Here's a detailed overview of the formation process of sedimentation. Steps in the formation of sedimentary layers. Weathering and erosion. Weathering. physical and chemical breakdown of rocks into smaller particles. This can occur through processes such as freeze-thaw cycles, plant root growth, chemical reactions, and biological activity. Erosion, the transportation of these weathered particles by natural agents such as rivers, wind, glaciers, and ocean currents. Transportation. Particles are carried from their source to a new location by wind, water, or ice. The mode of transportation influences the size, shape, and sorting of the particles. For example, rivers transport particles in suspension or by rolling them along the riverbed. Wind carries finer particles like sand and dust. Glaciers move a mix of particles of various sizes embedded in ice. Deposition occurs when the transporting medium loses energy, causing particles to settle out of suspension. The location of deposition can vary widely. Rivers deposit sediments in floodplains, deltas, and riverbanks. Lakes and oceans, sediments settle on the bottom, forming layers. Deserts, wind-blown sands accumulate to form dunes. Compaction. Over time, layers of sediments build up and the weight of the overlying material compresses the deeper layers. Water and air are squeezed out, and the particles are packed more closely together. Sedimentation. Minerals precipitate from groundwater and fill the spaces between sediment particles, binding them together. Common cementing agents include silica, calcite, and iron oxides. Lithification. The combined processes of compaction and cementation transform loose sediments into solid sedimentary rock. This can take millions of years. Types of sedimentary rocks. Clastic sedimentary rocks, formed from mechanical weathering debris. Examples include sandstone, shale, and conglomerate. Chemical sedimentary rocks, formed from the precipitation of minerals from solution. Examples include limestone and halite. Organic sedimentary rocks, formed from the accumulation of plant or animal debris. Examples include coal and some types of limestone formed from coral reefs. Factors influencing sedimentation. Particle size and density. Larger and denser particles settle faster than smaller, lighter ones. Energy of the transporting medium. High-energy environments, like fast-flowing rivers, can carry larger particles, whereas low-energy environments, like deep ocean floors, are sites of fine sediment deposition. Biological activity. Organisms can contribute to sedimentation by producing biogenic materials, like shells, or by disturbing sediments, bioturbation. Chemical environment. The chemical composition of water can influence the types of minerals that precipitate and the rate of cementation. Sedimentary structures. Sedimentary rocks often display structures that provide clues about the environment of deposition. Bedding or stratification. Layers of sediment with different compositions, grain sizes, or colors. Cross-bedding, angled layers within horizontal beds, indicating deposition in a current. Graded bedding, layers with a gradation from coarse particles at the bottom to finer particles at the top, often formed by underwater landslides. Ripple marks, small ridges formed by water or wind currents. Mud cracks, formed when wet mud dries and contracts. Importance of sedimentation. Geological record. Sedimentary layers provide a historical record of Earth's past environments, climate changes, and biological evolution. Natural resources. Many natural resources, including coal, oil, natural gas, and minerals, are found in sedimentary rocks. Soil formation. Weathered sedimentary rocks contribute to soil formation, supporting plant life and agriculture. Conclusion. The formation of sedimentary layers through sedimentation is a complex process that involves the breakdown, transportation, deposition, and lithification of materials. Understanding this process provides insight into Earth's history, the formation of natural resources, and the dynamic nature of our planet's surface. Types of process of sedimentation. Sedimentation processes can be classified based on different criteria, including the type of particles, the medium in which they settle, and the mechanisms involved. Here's a detailed breakdown of the various types of sedimentation processes. 1. Discrete sedimentation. Also known as Type 1 sedimentation, this process involves the settling of individual particles that do not interact with each other. This type typically applies to dilute suspensions where particle concentration is low, and each particle settles independently according to Stokes' law. Examples: settling of sand or silt particles in water. Removal of grit in wastewater treatment plants. 2. Flocculent sedimentation. Also known as Type 2 sedimentation, this involves the aggregation of particles into larger flocks, which settle faster than individual particles. This process often requires the addition of chemical coagulants or flocculants to promote aggregation. Examples: treatment of wastewater and drinking water using alum or polymers. Sedimentation in biological treatment processes where microbial flocks form. 3. Zone sedimentation. Also known as Type 3 sedimentation, this occurs when particles are present in high concentrations and settle as a collective mass or blanket. There is a clear interface between the settling particles and the clearer liquid above. The particles hinder each other's movement, resulting in a more uniform settling rate. Examples: settling in primary and secondary clarifiers in wastewater treatment plants. Sedimentation in thickening tanks for sludge treatment. 4. Compression sedimentation. Also known as Type 4 sedimentation, this happens when the concentration of particles is so high that the lower layers are compressed by the weight of the particles above. This process is common in the final stages of sludge thickening and dewatering. Examples: sludge compaction in wastewater treatment facilities. Settling of tailings in mining operations. 5. Differential sedimentation. Occurs when particles of different sizes and densities settle at different rates. This process can result in graded bedding, where layers of sediments show a gradation in particle size from bottom to top. Examples: formation of sedimentary rock layers in natural water bodies. Sediment deposition in river deltas. 6. Hindered settling. This is a collective settling process in which the presence of a high concentration of particles slows down the settling velocity of individual particles due to particle-particle interactions and increased drag forces. Examples: settling in thick sludge beds. Clarification in high-rate sedimentation tanks. 7. Gravity sedimentation. This is the natural process where particles settle under the influence of gravity alone, without any external force or chemical addition. Examples: sediment deposition in lakes, rivers, and oceans. Formation of geological sedimentary layers over time. 8. Centrifugal sedimentation. Involves the use of centrifugal force to enhance the settling process. This method is used when gravitational forces are insufficient for rapid sedimentation, particularly for fine particles. Examples: separation of fine particles in centrifuges used in laboratories. Clarification of oil-water mixtures in industrial processes. 9. Electrostatic sedimentation. Utilizes electric fields to enhance the settling of charged particles. This method is particularly useful in separating fine particles that are otherwise difficult to settle by gravity alone. Examples: treatment of industrial effluents containing colloidal particles. Separation processes in certain types of electrostatic precipitators. 10. Magnetic sedimentation. Involves the use of magnetic fields to settle magnetically susceptible particles. This method is used in specific industrial processes where magnetic particles are involved. Examples: separation of magnetic minerals in mining. Treatment of wastewater containing magnetic contaminants. Conclusion: the type of sedimentation process employed depends on the characteristics of the particles, the medium, and the desired outcome. Understanding these processes is crucial for designing effective water and wastewater treatment systems, as well as for applications in various industrial and environmental contexts.